to my channel. Um, yeah, so I'm not really sure how to start this video off, but I just want to, I guess, make a few lectures on math and physics, with the first video starting on probably the most important thing you need to know for AP Physics C, certainly at least for mechanics, and that is the work-energy theorem. And what this theorem states is simply that the change in kinetic energy of an object is equal to the net work done on that object from some points to another point. No, that's not accurate. Along some path, and if this net force is conservative, so if it's the gradient of some scalar value, then this is equivalent to the line integral of net force between 2 points. It doesn't matter what kind of path you take. So example of this in mechanics is gravity, gravity on a large scale, so between like two non-negligibly large planets that are, just like space, like the Earth and Moon, whatever. And then in E&M, that would be electricity. But whatever. This theorem simply states this. And today I'm going to be giving you two derivations for this theorem. One would be a little bit more intuitive. I'm not sure if really intuitive is the right word to use. Maybe more just scuffed. It uses a kinematics equation that's, if you've taken a regular physics class, you should have seen it, and you probably have it memorized. So let's start off with the first derivation. So first, this derivation is going to rely on a kinematics equation, as I said before, specifically that the change in velocity squared, not the change in velocity squared, the change of the quantity velocity squared, it's a very important distinction, is equal to 2 times the acceleration times the change in the displacement of the object under some time interval. And this is under the assumption that A is constant. And our space is one-dimensional. So it's pretty much just a line to say. Sorry for my handwriting, I'm not quite used to writing on a tablet yet. You can see it's a bit scuffed, but whatever, that's fine. So first we want to prove that this is true, and the proof is actually quite simple. So what we need to do is first to keep in mind that displacement over some time interval is equal to the integral of velocity over that time interval. In this case, we are assuming that A is constant. So for any time interval, any arbitrary time interval, change of t, delta t, let's say, so for any time interval delta t, we have that the change of x is equal to the integral of velocity over this time interval, starting at an arbitrary time points, initial time. And since our assumption is that acceleration is constant, that means velocity is a straight line, and that pretty much means that our integral is just the formula for a trapezoid. So that means change of x equals the initial velocity plus the final velocity divided by 2 times the time times oh god, I'm blanking out, sorry, times delta t, sorry. And we know that the acceleration will be given by Vf minus Vo divided by our time, just the change in velocity over the change in time. So we have these two, we've derived these two equations, and now it's very trivial to see that this expression holds. So let's just go to this next page, change x, yada yada yada, just write all this down. So we see very easily that's 2 times a time of acceleration times the change in the displacements is simply taking our equations here this value, and it's very easy to see using differential squares that's this is simply Vf squared minus Vo squared, which is just a change in velocity squared. So that is this kinemax equation, derived very simple derivation, but it's not the most important thing. It's just a lemma, like per se, for work energy field. So now we're going to ask a question. How can we find the change in velocity squared of an object that is undergoing a not non-constant force, a non-constant acceleration? Well, let's say that our object is being moved along some arbitrary path. So this might be this between 2 points, and well, now we're stuck because that previous kinemax equation was under the assumption that acceleration was constant, but since force varies here in this situation, we can't exactly use that kinemax equation, but we can zoom in very, very closely on some arbitrary points, on this path that this object will take, and we can very nearly approximate this zoomed in picture of this path to be a straight line. And along this path, assuming that our force is a function that is continuous, it's smooth, it's nice, doesn't have any sudden changes. If we zoom in far enough, it's very hand wavy arguments. It is. I should mention that this isn't really a proof. It's just intuition to why the work energy theorem is true. The actual rigorous proof will be in the next section of this video. But anyways, let's continue. If we look at this, if we zoom in here, not only is our displacement a straight line, it's a very small straight line, but also our force is constant under the conditions that the force is a smooth function, like a continuous function, whatever, which it will always be in physics. Usually it will always be a continuous or being nice function. So here our assumptions are met. Our change in displacement is just a straight line, and our force is constant along the displacements. So we can say that this that's the wrong delta. Sorry, that the change in velocity over this small, very, very small displacement is just 2 times the acceleration times the displacement, sorry. But we don't really, in our question, in the question we gave ourselves, we didn't know the acceleration, we only know the force, and so we need to get the force into this equation somehow. It's very simple. We just multiply both sides by the mass of the object, and then we just get this. And so the more we zoom in on this part, on this arbitrary point, on this path, the more accurate this picture will be, the more accurate this approximation will be. So in general, if we just do this at every point and then add up all of these approximations, we should get the change in velocity squared times mass of this object going along this path that is in some force field. And if this should sound very familiar, this is simply just an integral. So as we let x approach become arbitrarily small, we get m d v squared equals 2f dx. So now we just integrate this. We integrate both sides. Oh, sorry. Oh, this is so. Sorry about that. Sorry about my handwriting. It's very bad, I know. And we get, canceling out this integral over velocity and this velocity differential. Oh, this is wrong. Sorry about that. It should be squared. We get, and then dividing the entire both sides of the equation by 2, we get 1/2 m times the change in velocity squared is equal to, sorry, I should rewrite this, 1/2 times m times the final velocity squared minus the initial velocity squared equals to this integral of force over distance. So this is our proof, not a proof, our intuition, right? Wrong. This is completely wrong. This is utterly dog water, dog shit. Literally worse than my entire life. It's stupider than me. And that's really saying something. So, what's the problem with this? Well, let's look back at our original statement of the work energy theorem. I did not draw this out very clearly, but clearly there is a difference between how we combined the force and this this displacement differential in the true statement, and how we do it here. Specifically in this situation, we are simply scalar multiplying these two values. And this should already send some huge red flags through you, because displacement is not a scalar, it is a vector, and force is not a scalar, it is a vector. And this kind of operation is not well defined for vector quantities. So, what exactly did we do wrong? Well, what we did wrong was that we failed to account for the fact that our picture is not in one dimension. It is in two or three. It's in 3 dimensions, but for now, because of limitations of drawing on screen. Let's we'll just say we'll just use two dimensions as an example. So let's take our tiny picture again. We have this small displacement, which is a vector, and we have this force, which is a vector. And we can split this force into two components. So we can draw a new picture. We can split it into its components in relation to the direction of our displacement, our small differential displacement vector. This will be it's not I know it's not exactly along the y-axis and the x-axis, but we'll just do this because I can't really think of any other way to notate this. And this is a fact. So basically, we split the force vector into two new vectors, and we define fx, f subscript x, to be directed alongside the displacement vector, and f subscript y to be directed perpendicular to the displacement vector. And it's a fact in physics that any force or any component of force that is directed perpendicular to an object's velocity, displacement, whatever, won't change the object's velocity. No, sorry. It will change the object's velocity. It will not, however, change its speed. It will simply move the direction that the object is going because it's directed perpendicularly. For example, if we take this, if our force is always directed, if this is our object, and let's say it's this is our object, and we exert some force on it, and this force always stays perpendicular to the object's velocity. What will happen? Well, we can take a small time interval, so first will be pretty small, and so our object will shift a little bit. Its angle will change, but its magnitude will not change, because immediately as it does shift, the force will be redirected to be again perpendicular to this new velocity. And then repeat. What do you get? You get a circle with constant radius. Wait, is that right? Yes, that should be right. Yes, that is right. I'm stupid. Sorry. Oh no, I drew this incorrectly. You get a circle. Our object will travel in a circle or travel around some points, and its velocity will, oh my god, I drew it wrong again. Okay, so just ignore this. You get the rough idea. You know this, okay? Perpendicular forces on objects, forces that are perpendicular to object's velocity will never change its magnitude. And our kinematics equation here, this right here, is really about magnitude. It's not about direction. So keeping in mind that our picture is two-dimensional, so keeping in mind that the picture looks like this, the force that acts, the component of force that acts on our object at around this point is the component of the force that is parallel with the displacement vector, or in other words, the force's projection onto this displacement vector, which is displacement vector. I cannot speak. That is notated as f subscript x. Or if we define if we define an angle theta, that is the angle between our force vector and our small displacement vector, then we get that the actual force on that is contributing to this change in speed of, or the change in the magnitude of the velocity squared, not the direction. That component is f of x, the projection of f on dx, which, using our new defined angle, is the magnitude of the force. I should do this. Yeah, times the cosine of this newly defined angle. And you should recognize what this sorry. Oh god. Oh god. Sorry, I jumped ahead of myself. So the true actual kinematic equation for our zoomed in approximation around any point on this path is m change in velocity squared equals to 2 force. I'll just put the 2 on this side. Force, the magnitude of force x, times dx. Also notate this. And keeping in mind this equation down here, keeping in mind our newly defined angle at this point, around this point, we get this. And you should recognize what this is. This is simply a different way of calculating the dot product between two vectors. In this case, our vectors are the force vector and this small displacement vector. So 1/2. Sorry, this should not be delta. This should just be d. Sorry about that. Oversight on my part. So this is our actual equation between our relationship between our two differentials, and then integrating it again. Integrating this true. Actually, I kind of screwed up the order on. I kind of screwed up the time when I introduced the dot product, but it's fine. You understand. We do this, and we get the actual statement, and I kind of oh god. Well, I kind of blundered throughout this entire thing because I literally mentioned this at the start and I forgot about it, but we can't just define our path just by 2 points. There's an infinite amount of paths that we can take between 2 points. So this statement is actually not well defined, except for like, you know, this situation which you conservative force, whatever. So I kind of messed up. It's really just this. Just fix everything. Just when you just go rewatch. I mean, like, you get the points. Just keep in mind that there were multiple paths. There were infinite amount of paths you can take between 2 points, and depending on what your force is, if it's conservative or not, or if it's like a non-conservative force like friction, then each path that the object takes will give a different work. So this is the net. This is our statement from before. This is what the work energy theorem says. And what I did just before was some intuition on how exactly you can get to this statement. And now shortly we'll be going over the rigorous proof of this theorem.